So my name is Ulf Hansson. I'm working in the power management team, and this is supposed to be a training kind of session. So, and it's about device power management and idle. So yeah, feel free to ask questions anytime. So in particular, we don't want to waste energy when the platform or part of the platform is being idle. That's the main thing behind this. Yeah, what we want to achieve. So I want to go through a couple of frameworks that helps out with this in the Linux kernel, and I'm going to point out some use cases and deployments, and in particular also show a couple of good practices and tricks of how we can do this from this device power management point of view. So as I said, it's a training session, so feel free to ask questions at any time. I have around 20 slides, so it's not that much. So there is definitely room for yeah, discussions and questions. Perhaps a quick reality check, and who among in the audience here is like kernel developers, kernel driver developers? And who has been doing power management? A little bit. Okay. 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 Let's move on. And as I said, please interrupt if you want to ask something. So there is one framework or one way of dealing with idle, and that's the system-wide way of doing it. The system-wide sleep. So in this way, the entire platform is going to some kind of low power state in a controlled fashion, so to say. So the entire system is entering a sleep state, and this can be triggered from I mean two different ways. Either you have the user space thing, and it's like when you close the lid on your laptop, for example, and that means that the kernel gets notified from user space as I don't want the system anymore. You can put it in a low power state. And for you that have been working on Android, you know it's a little bit differently there. So that's there's some more mechanism inside the kernel to do this, and that feature is called auto sleep in the kernel. It's kind of a you can consider it as like a deferred timeout that keeps elapsing and keeps being rescheduled all over the time, and it checks if the system is ready to go to idle state. And if there's no one preventing it, it will go to this system-wide sleep state. And the way to prevent this is via so-called wake-up sources or wake locks, as they also mentioned this. And you can prevent it either by using in-kernel APIs or by using sysfs interfaces. So it's kind of two different approaches of how to go into these states. And there is different low power states supported by the kernel, and these are the main four, so to say. The suspend to idle, that's actually the newest one that's been introduced. It's quite a while now, but it's the newest one. And there's a suspend to standby, suspend to RAM, and suspend to disk. And there's a lot of common parts of the flow of how we enter these states, but there is also quite difference, of course. And I think the most common part that people are aware of is the suspend to RAM thing. At least in the ARM world, I would say that's the most commonly used thing. And yeah, what happens is in principle that the RAM is put in a self refresh mode, and everything else is being powered off as long as possible. And the lowest path states as possible. And in the suspend to disk, you will create like an image of the current state of the system and store that image to disk and power off the system. And when you do the repower on the system again, you will see that this image is there, and you will use it to restore the state of the system. So it means that you will be able to boot much faster than a fresh boot, kind of. So that's the I think that's the important part when you consider this a low power state. Suspend to idle is very similar to suspend to RAM. There's a different way how to dealing with the CPUs, but it's very similar to suspend to RAM in that sense. When you do enter the transitions, so to say. Any questions? Yeah. Can you take the microphone now? Microphone?
Go back, yes.
Yeah. It's not on?
Okay.
Yeah.
Can you explain this kind of system-wide sleep match to which part of power subsystem in kernel, I'll say, which part of power subsystem in kernel implement this kind of system-wide sleep functions?
Yeah. I'm coming to, in a couple of slides, I'm going to show a little bit more, but you can consider it like two parts if we really want to simplify how it works. There's this very I would say kernel-centric side of it that's implemented in /kernel, more or less, and that's where we take care of these common activities. Like when you start going to an idle state, you will have to freeze some tasks, and you have to freeze kernel threads, and you have to make sure userspace is not no more running, and so forth. Those parts is like the common part. And then we have all the I would say like platform specific things and devices, and that is going to that's taken care of by we call it PM core. I'm going to talk a little bit about the details of that in a while.
Can you give me a simple example about the suspend to idle versus suspend to RAM?
So the primarily difference is that in suspend to RAM, the core part is going to unplug all the CPUs except for the boot CPUs. So if you know about if you know about CPU hot plugging, that is exactly what is being used there. So you hot plug off those CPU, and then you idle the last CPU, and you're actually also calling SoC specific callbacks in that path. In the suspend to idle, you are relying on the CPU idle framework to put the CPUs in a idle state.
So the suspend to, have you measured the latencies involved in ripping out all the data structures, recreating the scheduler topologies and whatnot?
So I haven't done any measurement on that, but I can definitely imagine that there is improvement in using suspend to idle, because of doing these hot plugging things can be quite costly. So yeah. So if you have got things right in your implementation for ARM SoCs. In general, I would say, not every case. It would mean that going to using suspend to idle should be able to reach the same power numbers as suspend to RAM if you get it right, and you do it faster because you have less latency. So that's the ideal scenario would be that using suspend to idle. But I know that I mean there's a lot of vendors that don't use it yet, probably because of it's a ramp up time of knowing how these things work. So, yeah.
So why would the two schemes have been invented specifically to provide or to alleviate the deficiencies of suspend to idle or suspend to RAM? Like, why would they? Because it seems like we're doing two things to do the exact same thing.
So it's a legacy. So we started out doing suspend to RAM because we thought that was the way of dealing with it. But then we learned and realized that we can do it even better. Event to suspend to idle. So that's how it is.
So suspend to idle basically does DRAM refresh, same
Yes.
way that the suspend to run.
Yes.
Different framework.
Same frameworks.
Well,
It's a lot of code that's being reused in this pass. It's just the way how you deal with the CPUs.
Would it be useful to remove one?
Remove.
One of the scheme, because again,
Oh yeah. I mean, we probably want to use suspend to idle in the long run and get rid of the other part. But I think that's going to take some time because we are relying on all vendors to adapt to that and all SoCs and all platforms. So.
you can't do that for as long as even one suspend to idle is not as good as the suspend to RAM.
Exactly. So that's going to take time. Right. Okay, I'm moving on. I think I was here, right? I was touching about this user space thing, that how you trigger this, and this is just a slide to show how it actually looks, how the sysfs knobs looks like. So there is a sys power state knob, and you do an echo to that knob and instructing the kernel or what state to go to. And there's these different states there. The thing that I wanted to mention a little bit more about is the mem state, because it's a little bit more tricky than the other one. So mem itself is configurable. So it depends on what you have set this other mem sleep state to what state you will go to. So you can use these different states in that to decide what mem should mean. But it's quite neat. It works. For this in-kernel system sleep state, the auto sleep I was talking about earlier, there is a special state, and that's like a configuration. So if the auto sleep triggers and says that I want to go to a low power state, this is the state that we are going to enter. There is quite some documentation about this. It's available in the kernel, so go ahead and look at that if you want to have some more details here. But in general, I would say that when it comes to device power management, there is actually quite good good documentation in the kernel. So if you just have some energy to look around there, you will find some decent. Yes.
I think that I think as user, what you need to know is what is the typical use case for a user space. So what does Android do? What will a Debian server do? For example, what kind of things will it poke down in these files by virtue of that user space? It's one thing if I have my busy box and just echo stuff into the files, but what will the different common user lands do? That's my question.
So that is, I mean, it's configurable. If you look at like an Ubuntu desktop, for example, you have like there's like some settings dialogues when you can actually decide when my laptop is going without power, how should I do? And when I'm having the power cord in and it's been idle for 30 minutes, what do you want to do? So there is kind of this kind of settings interface. It's not actually mapping to these names. That's why it makes it a little bit confusing. But it's kind of what's happening in the background.
Do you know what Android does?
So Android is using autosleep, but that does not tell you what state that means, because autosleep is just system sleep.
Yeah, and then it's up to the device what it has configured in that sysfs file.
Exactly.
The autosleep file, right?
Yeah, exactly this one.
And that will be vendor specific typically.
Yeah.
Okay, I get it.
Yeah. Okay.
Not really, right? Because if you look at syspower state,
This one?
yes, freeze and standby is x86 specific, right? Or is it not?
No, no. Freeze is maps to suspend to idle. Ah, you mean there is a mapping to ACPI?
Yeah, the ACPI.
Yes, yes. So yeah, that is true.
So I'm guessing for ARM platforms, it's almost always echo mem, right?
that's how it should be.
Yeah. And then on the mem sleep state, again, it's probably suspend to RAM for almost everything right now because people haven't converted over to suspend to idle.
Yes. So that's typical.
Yeah.
Hello, yeah. So from ACPI S0 and S1 states you're trying to, is there any plan in ARM world to map them to something standard so that we can do more standardization of the states?
No, I don't think so. Or maybe there is, but I don't know. There is. Okay.
There's something called SCMI. When come to that talk, there's something called SCMI
Okay.
that helps you talk to a power controller directly. That has
Is
standard
that
interfaces.
in server space?
It's not implemented right now, but in the server space, it's mostly for clients right now.
Okay.
But that is about device power management. So it's
Device, system,
No, S is always for the system.
System
You're not
as
talking
well.
about device here.
devices, systems, everything.
Yeah.
Even systems, yeah.
okay.
Yeah. For all ARM platform, ARM 64-bit, for suspend to idle right now, we are reaching the deepest available C state. That's the default configuration. So suspend to idle is available for all the ARM 64-bit by default, and you will reach the deepest available PSCI or C state.
Yeah.
Unless you set up a PMQoS constraint.
Yeah. No, not for suspend to idle. You don't care about no. It's only look at the deepest C state. They don't care. The QoS the wake up latency that is used is the max value.
Okay. So moving into some of the more details, as Xunchan asked before. So I was talking about this common stuff where you do the freezing of tasks and so forth. But when it comes to the device power management thing, so if you're a little bit familiar with the driver and the device model in the Linux kernel, you know there is a lot of devices that's being created and maintained in the kernel, and all of these devices is added in a DPM list, so to say, a device power management list. And when you do the suspend thing, there is a bunch of callbacks that this PM core is going to be invoking per device. And assuming that we have like these 4 devices, it means that the prepare callbacks is going to be invoked for the I2C and SPI and UART MMC in an ordered way. And then when all the prepare callbacks has been invoked, it moves on to the next level, which is suspend and suspend late and so forth. And when everything has been, when all devices in this list and all these callbacks has been invoked, the device power management thingy is completed, so to say. And then there is some final things to bring the system into the low power state. And then, for some reason, you're waking up the system again, and there is like similar things that happens from a device power management point of view to resume the system. There's a set of other callbacks though.
how we divide the operation into the different callback functions. For example, that prepare, suspend, late, and non-queue. So, what's the methodology we can divide our code into the different callback functions?
So, if I understand you correctly, you're asking why these callbacks are so many and why those all exist, right? Yeah.
Exactly.
So again, it's legacy reasons. So if we had to redesign this, that would be probably one callback suspend and one callback resume, and you would probably provide, I mean, device specific and idle state specific in a different way. So this is something that has been growing, evolving over years, and we have ended up with this. And this is just a very minor subset of callbacks. There's different callbacks for hibernation, for example. It's a complete mess, but yeah.
So there's no work ongoing to try to.
I've been to a couple of conferences talking to these maintainer guys that's involved here, and I think we are all in agreement that we want to change this. We want to do it in a different way, but it's not an easy task.
Yes.
So. Maybe in the long run this will improve, but this is what we have for now.
I think there's like 20 callbacks or something, and just related to PM for the drivers.
Yes.
And it's very confusing.
I think from ARM point of view and from suspend to RAM, suspend to idle point of view, these 8 are the one that's important. And then there is I'm coming to a different framework as well, so there's an additional 2, I would say. So we have 10 that is important for us, so to say. All right. So moving on to the next thing here. That's the other framework that helps us dealing with idle. And we don't always want to put the entire system into a low power state. There is part of a system, devices in a system, that is, I mean, powered on, wasting power, but not being used. So this framework, it's called Runtime PM, provides you with these features of actually powering off these devices independently from other devices on a running system. So, and to do that, there is a bunch of helpers there. I'm not going to explain them in details, but there is reference counting available, and there is asynchronous and synchronous interfaces to power on and power off devices. And in principle, what you want to do from a driver and a system point of view, that you may have a request coming into your driver saying, please serve me with this request. And to be able to serve the caller with this request, you need to power on your controller or your device. And then you do this resuming. You do probably PM runtime get sync to resume your device or power on your device. And then you deal with your request. And then when you're done with that, you call a put API, say, I'm fine, just let my device go off now to save power. And in quite many cases, these requests tends to come in bursts. So you might get 5 requests in a row. And of course, if you power off a device, it means that you will introduce a latency when there is a new request, because you need to power on the device. So instead of always doing power on off for each and every request, you can add a little delay or an idle period, so to say, before you're actually powering off the device. And that's these auto suspend things. Don't confuse this with auto sleep. People tend to do that, and that's the system sleep stuff that we talked about before. So the auto suspend here is a Runtime PM specific feature that allows you to specify this idle period and deal with this, which is very convenient if you have bursts of requests to avoid this latency. Right? Yeah.
So apart from get sync and put, are there any other features available in the kernel for device auto suspending without that auto suspend delay, which is anyways a function of get sync and put? Is there any other third kind of mechanism today?
Not that I know of. then you have to do some, I mean, it doesn't make sense to have anything else because it will probably mean that you will reinvent the wheel again. So I know that there's vendor trees out there and having like using delayed work to do this kind of stuff, but this should suit your needs. If it doesn't, probably you need to expand it.
Is there a sysfs API to control each and every one? And is there some kind of dependency of the device?
Yes.
So once you power down one, it powers down the others?
Yes. So the Runtime PM infrastructure code respects two things from a dependency point of view. One is this parent-child story. So if you power on a child, the parent will always be resumed while the child is resumed. But there is also something that's called device links, and that's a framework where you can specify functional dependencies between devices. So if there is one device depending on another, this Runtime PM infrastructure code will also make sure that my functional dependency device is also resumed. That's the same thing for this system sleep thing in the PM core. That's also being respected there.
Sorry.
Can you give an example of such a device dependency?
Of the parent-child thing?
Not parent-child, like not a controller and a device, but
okay.
like you know, the other one, the other kind.
So I think one typical use case is like if you have a device having it needs to have a clock enabled to be able to run, but that clock might be behind some I2C bus or something. And to be able to run, you need this I2C device to be up. So that's could be a case.
So currently in upstream for get and put calls, so whenever we pass a device which probably doesn't have runtime PM enabled, if you call runtime get or put, you actually get an error code which is quite vague. So the interpretation of that error code is like probably it gets inval or something like that. So
yeah.
Are you going to fix that, or do you think that should go into the PM core? Because there's lots of wrappers to many drivers actually, not just one. At least 32 instances in the kernel. So do you think that makes sense to actually PM code to return like no support or some?
Yeah, we could probably explore that. I know there is a bunch of drivers that actually tries to deal with this error code properly, but it's not obvious of how to do that. So it tends to be it's easy to get wrong. That's what I'm saying.
Yeah, that's why I think lots of code has like
at
least a few lines of wrappers.
It's a good point. It's something that we could look into to improve. I'm not exactly sure how to do it, but yeah.
Okay, cool.
So if I remember correctly, the runtime get sync or runtime get cannot sleep, right? Or it can sleep?
So it depends on how you have configured the runtime PM. When you do the initialization of your runtime PM deployment, let's say from you call this PM runtime enable, for example.
Yep.
There is an API called PM runtime IRQ safe.
Okay.
And that instructs the runtime PM core that this is a device which callbacks might be executed from atomic context. So
okay.
you can do that.
We can do that.
Yes. Yeah. Right. Okay, I think we are actually walked through this already, but just to mention that these callbacks I talked a little bit about before. There is specific callbacks for this runtime PM thingy as well, and these are called runtime resume, runtime suspend. So yeah, this is the typical flow. What happens? You do a get sync because you need to do something. It means that the resume callback will be invoked, and then you will. Sorry, yeah. The resume callback will be invoked, and in that callback you do the power on of the device. You do some work, and then you do put, and the suspend callback will be invoke to power off the device. Yeah, so this is the callbacks we've been talking about. It's a bit messy, but yeah. Anyway, so these callbacks are all contained in a struct dev PM ops, and just remember that for a couple of slides going ahead. Things can go a little bit more complicated. So there is more complex topology there. It's not like every device is completely independent from other devices. Some devices may actually share resources with other devices. And for example, here I've drawn a picture where there is a power rail that's being shared among a couple of I/O devices. And to manage these kind of complex topologies, we have invented something that we call PM domains in the kernel. And that is something that applies to both the system-wide scenarios and the runtime PM scenarios. And to deal with this, you easily understand that we need some kind of hierarchy here to represent this. And that's what we have. So in this struct device, we have a set of structs, and there is something that's called driver, of course. I think we all know about that. And the driver can have these struct dev PM ops I was talking about earlier. But that can also be on a level above, which is the bus. And the highest hierarchy in the level is the PM domain. It can also have these struct dev PM ops. So it's like a hierarchy of callbacks. So it's not just one set of callbacks, it's like a hierarchy of callbacks. It's even more complicated than this. So if you said we had like 40 callbacks, that means like we actually have 100 and a bunch of callbacks. It's quite insane. So one of these implementation of PM domains that I was talking about is ACPI. I'm not going to go into details, but I want to mention a few things here that's important for us to know about. So the ACPI is like a firmware-driven interface of how to control power management, and that's not. I mean, that's not specific, so to say. But the thing is that's specific is that it's almost everything is known by the firmware. So it's so it's like a very centralized view of dealing with power management, so to say. And there's nothing bad with that, but this is what we're being used on x86 for a long time and on ARM servers. And so that's something that we can keep in mind when we move ahead and think about the other deployments of power domains, which is completely have a different mindset of how we implement this. So both the ACPI PM domain obviously supports both runtime PM and system-wide sleep. This moves into the other deployment of power domains, and that's the generic power domain, aka Genpd. That's one of those infrastructure that me personally is maintaining in the kernel. And its intent is to provide like a generic and flexible way of letting SoC and platforms implement these power domains. And it gives a bunch of features, and you can have like a nested way of describing these domains. So you can have like a hierarchical way of having domains. Not only devices can be hierarchical, but also the domains. And it allows you to register provider-specific callback, so to say. So to deal with these power domains, you can power on power domains and you can power off power domains, and and so forth. So and Genpd gives you give you this infrastructure code to register these platform-specific providers, so to say. What it also does is that it helps to deal with this attaching thing. So when a device gets probed, the kernel or a couple of different buses, subsystems, ask for their devices to be attached to a potential power domain, and that's where all this magic happens in the background. That this dev PM ops I was talking about earlier is going to be hooked up to this PM domain on that level, so to say. So that's kind of what happens in the background when a driver probes, without the driver also actually having to care about it. What it also supports is that you can have, you can even have multiple devices having, a device can even have multiple PM domains, which is a kind of a new thing. I'm not going to touch that on this training. It's something that deserves a separate slot, I think. Another thing that's also supported by Genpd is something that we call performance states, which is related to DVFS, dynamic voltage frequency scaling, but that is also a separate slot to talk about, so some other time. Yep.
So for Genpd, what is there is that you have an on state and you have an off state for a power domain, right? And certain domains might be where you have intermediate states, wherein there are intermediate retention states. So why on and off? Why have the others not been provided?
You have both. So Genpd supports multiple idle states. So it means that you can, I'm going into that in a couple of slides.
Okay,
that there's a governor there, but it's, you can specify when you register your Genpd provider, say that this is my provider and it has 4 off state or 4 idle states. Okay. So this is like what you, this is this supported in Genpd from a device tree point of view. These bindings are there and are free to be used. So you can actually specify the PM domain topology here. You can specify the PM domains, and if you have a hierarchy there, you can specify that. And for each of the devices that you have, device nodes, you can instruct what domains these devices are going to be attached to. So it's quite convenient, and this is just a simple example. There is, of course, documentation for these bindings that you can have a look at, and there's a lot of examples as well.
Is there some way to have like more than one parent? Let's say, so parent. So if you have one link, let's say is shut down, or you have some kind of counter, so only once it's zeroed out, the power domain really shuts down.
Yes, all that is managed internally by Genpd, reference counting and all that stuff. So for this case here, for example, it means that, I mean, if there is one of these devices that is active, of course you cannot power off the domain, and that's the whole thing what Genpd deals with.
What would be the state of the device when we do a power domain down? So would it, in terms of device hierarchy, would it actually tear down the device totally, or?
So if we talk about the runtime PM case, so let's go back. So if we talk about the runtime PM case, that means that all of these 4 devices may have different drivers, of course, and these drivers may have deployed runtime PM. So there's a lot of get and put being done on these different devices.
Yeah.
So when any of these devices are runtime resumed, it means that the power domain for all of these devices are on. When all of these devices goes off, or well, the last device goes off, there is already 3 off and the 4th also goes off, Genpd sees that now all my devices that are attached to this domain are off. Then I can power off the entire domain.
Yeah. So what would be,
yeah. So vice versa happens when you do the power on, of course. So if there's no devices that's on, I need to power on my power domain first.
So the device instance, even in the power down state, will be there. It's just marked as
off,
inactive or whatever.
Yes.
So doesn't it make sense to tear it down because there's no power rail at all?
Tear down the device or the
device itself?
So it's actually the opposite around, I would say.
So it's as good as removing the power from a device, isn't it?
I'm not really sure what you're.
So we have that.
You have to define what you mean by tearing down the device.
So
is that releasing the memory for it?
No. So we have let's say we have a use case wherein.
If we look at this slice, maybe it helps.
Yeah, so what we are trying to, I'm trying to understand is that we have a use case wherein we have a DSP and there's some processes running in the DSP and they could dynamically go down and come up, right? So I was thinking, could we attach it to runtime, power domains and get it working, or should we really tear down the device when the power down happens on that remote side?
So if you have is it one device or is it several devices?
There are multiple services actually. So
yeah, so then you have to figure out if there are some dependency between the devices, or there are some dependency from, parent-child point of view, or are they sharing some power resources? So if they're sharing power resources, you should have a power domain. I mean, I'm not saying that they are sharing a clock or something that can be managed to the clock 3. But if they share like a power domain, they're on the same island, so to say, if they have a power rail, for example. That's a good argument for having a power domain. And if they're just parent-childs, just implement the callbacks on the driver or the subsystem level. That should be sufficient.
Okay, yeah. I'll talk to you.
Yeah, we can. So, just wanted to mention a little bit about this governor I briefly mentioned before as well. So, when we do this power off in runtime of a device, we obviously need to resume it, power on it when we are going to use it again. And that introduces a latency, like a request latency kind of. And in some cases that's completely, it doesn't matter because the time to resume the device is so quick, so it doesn't care. And but in cases when it does matter, there is 3 ways to mitigate this problem. And I've already mentioned this auto suspend thing, where you can deal with burst requests. You don't have to do this up and down between every request. But in the worst case scenario, you have you cannot accept any latency at all, and then you can just resume the device and keep it on until you're ready with your use case or whatever. But there is also a third option that's a little bit more fine-grained, so to say, more flexible. That is that for each of these PM domains, you can attach a governor to it, and that governor monitors so-called dev PMQS latency constraints. So for each device in the system, there is a user space, a sysfs interface for user space, where you can specify these latency constraints. And there is also in-kernel APIs to do this. So when this device is going to is being requested to be powered off from the runtime PM point of view, this governor is going to kick in and say that, there is actually a latency request set on this device. I'm not going to allow it to be powered off. And so it just bails out and says that it's still on. So that's the principle behind this. What?
Does it do more fancy stuff, or it's just on?
So there is 2 things here. There is from a runtime PM point of view, there is only on and off. But from the power domain point of view, as we do support multiple idle states of the power domain, the governor is checking these latencies per idle states of the power domain. But that is like in the second phase, when all devices is going powered off. Can we power off the domain as well? So the governor is taking that into consideration as well. Yeah, so this is the flow. What happens if you have a power domain, a Genpd attached? I think we have walked through this already. So just let me take it briefly. So the resume callback of the device is now having a Genpd callback assigned, and that means that this Runtime PM core is going to look at the highest hierarchy and find this callback and invoke that one. And then it's up to Genpd to do the right thing. And if it needs to power on the domain, it does that. Then Genpd is actually looking below in the hierarchy. And in most cases, at least for the platform device cases, there is no other runtime suspend callbacks assigned. It's optional, of course, but it's only on the driver level. So there is no on the bus layer, for example. So that means that Runtime PM will actually find a resume device on the driver part and invoke that, which gives the driver the option to do the driver-specific stuff. For example, enable a clock or reconfigure the pins, so to say. So that's what's happening in the background. When you call this PM runtime get, there is a whole flow of things that's happened. Yes?
Do you have some use case where we have some Genpd callback and a bus registered?
Whereas callbacks on every layer?
Yeah.
So yes, there's this AMBA bus.
Okay.
So in the AMBA bus case, there is a bus clock that's being managed by the AMBA bus. So that's one of those cases. And in that scenario, it means that Genpd is going to call that runtime resume callback, if we're talking about resuming, of the bus. Then it's up to the bus to continue calling the driver callback. So there might be several layers here in between. Okay? So a couple of words about wakeups. There's something that we call remote wakeups, and that is wakeups in regards to Runtime PM. So when you go into this runtime suspend state, you might want to be able to wake up for some reasons when there is something happening on the external bus, so to say. And so typical use case is that you might have a UART and you want to wake up and there's some hammering on the console, for example. And there's a whole bunch of different stuff that's you might want to wake up. There's Wi-Fi drivers using SDI or IRQs, for example, and so forth. The thing here is that when it comes to remote wake-ups, those are always, if you support them, if your device and driver support them, you shall always configure them when you go into runtime suspend state. That's a rule that you should remember. And if you need these remote wake-ups, but your device is not capable of supporting them, the only thing that you can do is to keep being runtime resumed. So that's a limitation that we have. And there's it depends on the SoC how they support these wake-ups. And there is a really good helper here to achieve this wake-up thingy. That's this dev PM set dedicated wake IRQ. I'm not going into the details behind that, but the important thing is that it actually does most of the things that you in general need to support this. So if you're you should look into that in details if you are going to implement support for remote wake-ups. when it comes to system wake-ups, it's a little bit more to it than for remote wake-ups. So system wake-ups is like typically like you have a button that you press, you want to wake up the system, and yeah, the same thing might be for UART. The whole system is sleeping, but you want to hammer the console and you want to wake up the system. That's typical system wake-ups. And yeah, wake on LAN, I think we know about. It's a complicated thing, but that's one of those things as well. What you need to do to support that is that you have the driver needs to announce that it supports this kind of wake-ups, and that's that's the first thing that needs to happen, as this device init wake-up thing. And then there's actually a different mindset here, saying that it's not really the driver that decides if I'm going to have this enabled when I go to this system sleep state. That is the user space decision. So the driver's responsibility only to announce what it supports, and user space tells if I want it enabled or not. So that's why there is this device may wake up interface, which you typically should call from your system suspend callback, and that gives you the information if I should have the wake up enabled for my device or not. And then if it turns out that I need my wake up to be enabled, then there is APIs called enable IRQ wake to do this, to inform the infrastructure about this. And again, it's actually the same helper that I was pointing to before. This dev PM set dedicated wake IRQ that helps a lot with dealing with this IRQ. And for this particular case, it means that this IRQ, there's a separate IRQ handler, and this PM core I was talking about that call all these device callbacks actually deals with the wake-ups automatically behind your back, so to say.
The previous slide, why do you call them remote wake-ups?
Because it's about runtime PM. I have no idea why they call remote wake-ups. Someone have decided that is the terminology that we should be using, so that's why I'm sticking to that.
Okay.
Yeah.
The previous one, so let's say wake up on LAN would wake up first the PHY or the MAC, but only then it will wake up the whole system if needed, right? So
yep.
You have like wake on LAN is just like used here, but then it propagates up to the system level, right?
So this is about when the system is awake.
Yeah.
So the system is not sleeping here. It's only devices that are sleeping, or part of the system that is sleeping. So only that part is going to be woken up if they are sleeping.
Right. Okay.
So in the other part here is when the whole system is sleeping.
And the device itself.
And the devices also. Yeah. So yeah, there is definitely terminology that can be approved about this, but since this is the common terminology, I don't want to change that now. But it makes sense to simplify this. Okay, some words about the Genpd in regards to this as well. There is a configuration flag that you can set for your Genpd provider, which means that if there is any of the devices that is in your Genpd that's attached to your Genpd, you may, and that has wake-ups configured during system sleep, you may need to have the power domain to stay on, because if you power off the domain, you will lose the wake-up. So this active wake-up flag helps with that. That's the main thing I wanted to explain here. And so for the scenario where you want this, you add this flag, and you do that at per Genpd level. And when you start looking into the details, you will realize that there is limitations here. For example, depending on how you route your wake up, you might you might want to have the wake up enabled, but you don't require the power domain to be on for some devices, and for others you need it. And if you have this kind of more complicated ways of depending on how the SoC looks like, there is no way to deal with that in a fine-grained manner. It's like all or nothing. So either you have this flag for all devices or none devices. So it's not really fine-grained enough. Any questions on that?
So I just want to clarify. If you set this flag for one device, you set it throughout the SoC. So that what means is that you cannot turn any of your power domains off.
You set it per power domain.
Yes.
So not per device, you set it per power domain. But there may be several devices sharing the same power domain. So it means that it applies for all devices that in the same power domain. Yeah. Right. I have a couple of more slides, but that's going to be for different other training sessions. So I think I'll stop here.
So what's the current state of how device state is managed when you are runtime? So if you are runtime suspended a device and then you try system suspend, are you going to resume that device and then put it back to suspend? I mean,
no, not if you do this. So just 1 minute briefly about this then. Okay. So it's very common where you actually have the very similar states. So doing runtime suspend is very similar to doing system suspend for a device. So historically, there was no way to deal with this. So what you have to do when you do the suspend, you actually had to do runtime resume the device, and then you have to power off the device. It's completely crazy. So wasting time, wasting energy, and whatnot. So we invented something that we call Runtime PM centric approach. And in that path, you'll take these kind of things into account. And there's two helper functions that you should be aware of. And that's called PM runtime force suspend and PM runtime force resume. And you can, in principle, what you do is that your system sleep callbacks, your system suspend and resume callbacks, either you just assign them to these helpers or you call them from your callbacks. And within those callbacks, you take into account if my device is already runtime suspended, then I'm done. If it's not suspended, use the runtime callbacks to invoke my callbacks to suspend it. And the likewise is for the resume part. So you are reusing code and you're also avoiding to resume devices when not needed. So the good thing here is that we only had 1 minute to talk about this, but there's 120 users of this in the kernel. So there's plenty of good references. This is something that you really should pay attention to when you do the deployment in your drivers. It's really, really important, I think. Okay. This is the same, it's following the same semantics as the existing frameworks. Yeah, no, this is following the topics or the hierarchy. Yeah. Thanks, everybody.